Now let's see the nth order differential equation. So we have discussed about two types of differential equations. One is ordinary differential equation and the other is partial differential equation. So coming to the ordinary differential equation, which is nth order ordinary differential equation, which we're going to discuss in general form. Is what we're going to discuss in its general form. So what is an nth order ordinary differential equation in general form? Let's see. Suppose I write the differential equation in the form f of x, y, dy by dx, d square y by dx square, and so on and so forth, d power n minus 1 y by dx power this, and d power n y. Then this is called the ordinary differential equation of order n, which is this. If suppose I take dy by dx as y dash or y power 1 is what we denote for this, and d square y by dx square is denoted by this, and so on and so forth, where d power ny by dx power n is denoted in this form, then this reduces to f of x, y, y dash, y second derivative, y nth derivative is equal is how we define the nth order ordinary differential equation consisting of x, y, y dash, y double dash, and nth derivative of y equals 0. So order n. This is the general form of representing the nth order ordinary differential equation f of x, y, y dash, y double dash, so on and so forth till nth derivative of y equal to 0. Now next, let's see how a differential equation where the solution set of the differential equation represents the family of curves. Solution set of differential equations, which is represented as family of curves. So let's see how the solution set of differential equations represents the family of curves. For example, I take y equals mx, then the corresponding differential equation of this is obtained by differentiating on both sides. With respect to x, we get dy by dx is m times of d by dx of x, which is m. So dy by dx is m which I'm going to substitute in 1. So substituting in 1, I get y equals m, which is dy by dx of x is what we get. So this is the differential equation which I have obtained for the 1. That is, 2 is the differential equation of 1, that is the original function y is equal to mx, or original equation of curve y equal to mx. And not only that, 2 the solution set of 2 of this equation 2 represents the family of straight lines, because the solution set is y equal to mx and it's a straight line passing through origin, represents the family of straight lines passing through origin. Is how we understand the solution set of differential equation connected with the differential equation itself. With the example problem y equal to mx, when I differentiate on both sides with respect to x, I get the differential equation y equals dy by dx times x, which is called the differential equation of the corresponding equation 1. And therefore, the solution set of 2 represents the family of straight lines passing through origin. The solution of this is this, which clearly is a set of all lines passing through origin in the form all the lines passing through origin, etc. So we have all the set of lines passing through the origin, the family of curves connected with the solution set of differential equation. Now next is about forming a differential equation. So let's see how a differential equation is formed from the general equation given out there. So the topic is about forming of a differential equation. So this process generally involves elimination of the arbitrary constants. That is, the forming of a differential equation is solely dependent on eliminating the arbitrary constants. Is how we understand the connection of forming of a differential equation to that of eliminating the arbitrary constants. So let's see how we can just solve this. Say for example, I have an equation y equals ax plus b. Now this differential equation has two arbitrary constants, or let me take ax squared plus bx plus c. So this differential equation has three arbitrary constants, ax squared, ab and c. So here a, b, c are the arbitrary constants. So our target now is to eliminate a, b, c, the arbitrary constants of the equation. So in order to do that, initially I differentiate both sides of the equation, which I represent with 1. So let me take this as equation 1 and differentiating 1 with respect to x, I get dy by dx equals 2 times of ax plus b, because d by dx of x squared is 2x and d by dx of x is 1 and d by dx of a constant is 0. Therefore, I don't have c, which is totally eliminated. Now this is equation 2, which I have obtained. But now again I differentiate 2 with respect to x. I differentiate this equation and see what would be the next differential equation I obtain with respect to x. Differentiating 2 with respect to x, I get this as d by dx of dy by dx equals d by dx of 2ax, which is 2a, and d by dx of b, which is 0 because it's a constant. D by dx of x is 1, so I get this. And therefore, this would be d squared y by dx squared equals 2a, because d by dx of dy by dx is d squared y by dx squared. That is the second derivative, which we generally denote with y part 2 is equal to 2a. And this is equation 3. Now next, I would like to find the value of a from this equation. That implies a is second derivative of this by 2, which I substitute in equation 2. Substituting in 2, we get dy by dx equals 2a, that is this of x plus b, is what we get when we simplify. So here we get a differential equation in the form d squared y by dx squared times of x minus dy by dx plus b equal to 0, where b, the arbitrary constant b, cannot be eliminated for this particular quadratic function, and hence we get the answer in the form x d squared y by dx squared minus dy by dx plus b equal to 0 is the corresponding differential equation for the given equation y equals this. Now let's see another differential equation where we can eliminate all the arbitrary constants. Say for example, I have the question which says form a differential equation for y equals a cos 3x plus b sin 3x, where here a and b are the arbitrary constants which need to be eliminated for forming a differential equation. So in this, I have the differential equation this, which I take as equation 1. So y equals a cos 3x plus b sin 3x is equation 1. Now I differentiate both sides of equation 1 with respect to x. So differentiating 1 with respect to x, we get dy by dx equals a times of d by dx of cos 3x is minus 3 sin 3x using the chain rule, and this comes out as b times of 3 cos 3x, again using the chain rule. Now this gives us dy by dx equals 3 times of minus a sin 3x plus b cos 3x is what we get when we differentiate on both sides. Now let me take this as equation 2. Now next, it is now that we are going to differentiate this and see what happens in the second differentiation. So in the similar process as I differentiated 1 with respect to x, I'm going to differentiate equation 2 with respect to x. Differentiating 2 with respect to x, we get d by dx of dy by dx, that is d squared y by dx squared, is 3 times of minus 3a cos 3x, and this in the chain rule gives me minus 3b sin 3x is what we get. That implies d squared y by dx squared on taken common gives us minus 9 times a cos 3x plus b sine 3x. Now a cos 3x plus b sine 3x is y, which I'm going to substitute in terms of 1. Therefore, this is minus 9y, since from equation 1 is substituted with y out here in the right hand side. Therefore, we get an equation which is d square y by dx square and plus 9y equal to 0, which is nothing but it's an ordinary differential equation. It's an ordinary differential equation of order 2, or it is called the second order differential equation of the corresponding differential equation for the corresponding curve y equals a cos 3x plus b sine 3x. So every function or a curve is associated with its corresponding differential equation, and clearly it is very important to identify that in this curve which has two arbitrary constants, then the order of the differential equation will be 2. If the number of arbitrary constants is n, then that differential equation will have order n. So the order of a differential equation is associated with the number of arbitrary constants in the curve. So therefore, in order to eliminate two arbitrary constants, I differentiate the equation twice. In order to eliminate three arbitrary constants, I differentiate the equation thrice, etc. So ordinary differential equation of order 2 for the equation y equals a cos 3x plus b sine 3x is d square y by dx square plus 9y equals 0. Let's see the learning outcome in forming of a differential equation. Now, as we have seen that if there are n arbitrary constants, implies nth order differential equation is how we understand the connection between the number of constants of the given family of curves and the order of the differential equation. So n arbitrary constants implies nth order differential equation is the learning outcome of this. And the second learning outcome is that every equation or every curve has its corresponding differential equation. Every curve has the corresponding differential equation is how we come out with the next learning outcome. So the two learning outcomes for the case of forming of a differential equation is that 1, n arbitrary constants implies the order of differential equation is the number of arbitrary constants, that is nth order differential equation, and every curve or any equation has the corresponding differential equation, which is obtained by eliminating its respective constants. Next is the solution of differential equation. Now that we have discussed about differential equation, now comes the biggest question, and how do we get the solution or how do we solve the differential equation? So the topic is about solution of a differential equation. Now, what do we mean by solution of a differential equation? In general, we know that a differential equation is an equation which involves one dependent variable and one or more independent variables. So the value of that dependent variable is nothing but which satisfies the given differential equation is called solution of a differential equation. So the definition says the value of the dependent variable which satisfies the given differential equation is called the solution of that differential equation. So the value of that dependent variable which satisfies the given differential equation is called solution of that differential equation. Is how we understand the solution of given differential equation. Now there are two types of solutions for the solution of a differential equation. So let's see the two types of solutions. Every solution of a differential equation is said to have two types. One is the general solution, and then it is the particular solution. So in these two types, let's see how we define each of them. General solution is a solution in which the number of arbitrary constants is equal to order of the differential equation. Then in this case, we get the solution in which the number of arbitrary constants is equal to order of the differential equation is said to be the general solution. Now, particular solution is the particular values which the arbitrary constants, the particular values for which the arbitrary constants are substituted with given in the general solution is called the particular solution. So these are the two types of solutions which we're going to discuss exclusively through an example problem. The solution of a differential equation is classified into two types. One is the general solution and the other is the particular solution. As we have seen with the solutions of differential equation classified into two types as general solution and particular solution, let's see some related problems. So in this case of, for example, as we have taken in the previous case, that this differential equation of order 2 had the general solution, as we have already solved, as y equals a cos 3x plus b sin 3x. This formed into, by eliminating the constants a and b, the respective differential equation was this. Therefore, this is called the general solution for the given differential equation. Now let's see how a particular solution is obtained. Let the arbitrary constant be fixed as sum a equal to 1 and b equal to 1. That implies we get y equals cos 3x plus sin 3x, which is called the particular solution of the given differential equation. That means we give the particular values for the arbitrary constants fixed at a equal to 1 and b equal to 1, say for this example problem, then the general solution with substituted with arbitrary constants reduces to y equals cos 3x plus sin 3x. So for the differential equation d square y by dx square plus 9y equals 0, the general solution is y equals a cos 3x plus b sin 3x, and the particular solution is cos 3x plus sin 3x. Next is the learning outcome. So what is the learning outcome from the two types of solutions which we have seen? The learning outcome is that if I take the general solution represents family of curves, and this particular solution represents fixed curve, and the general solution has arbitrary constants involved. Involves arbitrary constants, and this does not involve arbitrary constants. So the learning outcome for general solution is that it always represents family of curves and it involves arbitrary constants, and particular solution is a particular or a fixed curve and it does not involve arbitrary constants. General solution and particular solution have their own respective definitions, is how I understand the learning outcome. Now let's discuss solution or solving of a differential equation. In this case, we take exclusively first order and first degree differential equation. So we know that a first order first degree differential equation is generally represented in the form dy by dx is equal to f of xy, where y is dependent variable and x is an independent variable. So this is of order 1 and degree 1, and y is the dependent variable and x is the independent variable, is how we differentiate between this and this. So the reason we have considered the first order and first degree differential equation is that we're going to discuss the solution of the differential equation of first order and first degree. Of higher orders is beyond the syllabus, but the present syllabus of the session deals with first order and first degree differential equations and its respective solutions.